simple gas laws. So gases have four basic properties, which translates to four variables in the equations. There's pressure, we call that capital P, volume is capital V, temperature is capital T, and amount in moles is not capital M, because what's capital M? Moles per liter. So moles is N. Sorry. Moles is N. These properties of a gas are related. If you change one, it's going to affect at least one of the others. So we're going to talk about three simple gas laws, and these simple gas laws are just relationships between two of the variables. So a guy named Robert Boyle, he lived back in the 1600s. That was a heck of a long time ago. I do not need you to remember his name, okay? But he did some awesome things, so we're going to talk about him. He used a J tube to measure the volume of a gas sample at different pressures. So here's the J tube, and he's got a gas in here, and this end of the tube is sealed. So he can figure out what the volume of the gas is, and he can figure out the pressure by looking at the heights of the columns of mercury, measuring the difference with a ruler. Well, if you pour more mercury in here, that's going to push down on this. Gases are compressible, and it's going to cause the volume of the gas to get smaller. And if we look now at the heights, the height difference is larger. That tells us that the pressure inside has increased. So we see that the pressure increases as the volume decreases. This is called an inverse relationship. One goes up, the other goes down. So what a scientist will do is they will do stuff over and over again and change things up a little bit. And so this is a Boyles Law Experiment, where you've got a gas sample and you're changing the pressure, so you're increasing the pressure, you're measuring the volume. And this is what happens. You start with a volume up here, maybe 420, whatever unit that is. It should have a label, but it doesn't. As you increase the pressure, the volume decreases, and it makes this curve. Okay, so that's a nice curve. We like straight lines, though, because we can make an equation for the line. So Boyle's law, very simply stated, is this, that the volume is proportional to 1 over the pressure. And that's provided that you keep the temperature constant and you keep the amount of gas constant. So we just saw that the graph of volume versus pressure is curved. But if we graph volume versus 1 divided by the pressure, so here's a graph of volume versus pressure. This is data I just made up. I labeled. We get that curve, but if we graph volume versus 1 over the pressure, take all those pressures and invert them, now we get a beautiful straight line. And we see that there's a direct linear relationship. We love stuff like that. Another way to state this is that the pressure times the volume of a gas is equal to a constant. Or if you have one pressure and one volume, you multiply those, and then you mess around with the pressure, the volume will change in a way that that's still constant. So this is what you should remember as the relationship between pressure and volume. P1V1 equals P2V2. You don't have to remember the top part, no. You don't have to remember this. There might be some questions, though, that say, well, if the pressure increases, what happens to the volume? It decreases. So this is where balloons come in handy. We've all had some experiences with balloons, right? If you put pressure on a balloon, what's going to happen to its volume? Think of, well, if I was able to get my hands around it so that I could really just squeeze it and put pressure on it, is it going to get bigger or smaller? It will get smaller, right? And if you reduce the pressure on the outside, it will get larger. So it's an opposite, an inverse relationship. Let's think about what's happening in terms of the molecules. So we're going to see things like this a lot. This is like a piston, a container where the lid is movable and it's gas tight. This one has a pressure gauge on it so we can read the pressure. It's a modern type of thing. So here we have some gas particles in here, and we've got a 1 kilogram weight on top pressing down on it. And we see that the volume of this gas is 1 liter and the pressure is 1 atmosphere. If I put a heavier weight on top of the gas, that's going to press the lid down, right? And it's going to compress the gas. So now the gas has a smaller volume because I put pressure on it. I pushed on it. So the volume has gone down by a factor of 2. It's half as big. And the pressure went up by a factor of 2. And if you think about what these particles are doing in there is less area, right? So they're going to hit more frequently. There's going to be more pressure. Does that make sense? You can also think about, say, kindergartners in a classroom. And so here are the kindergartners, and it's right after the Valentine's Day party, and they were eating cupcakes and sugar. And so they're running around the classroom, and the pressure would be the equivalent of them running into each other, running into the walls, right? Now, if you corral them and confine them to half of the classroom, are they going to run into each other more often? Yes, they will. It's not going to slow them down. They're just going to keep running, and they'll run into each other. More pressure, smaller volume. Boyles Law has some implications for scuba diving. So up at the surface, right at the surface, let's say this is the ocean, the sea. At the surface, I am at sea level, right? What's the pressure up there? 1 atmosphere. As you go down into the water is putting pressure on you. Water's a lot more dense than air, and so you notice the pressure difference. If you've ever dived trying to get something off the bottom of a pool when you have an ear infection, you are very much aware of the pressure that's being put on you by the water. Every 10 meters that you go down, you get about 1 atmosphere of increased pressure on your body. So if you go down to a depth of 20 meters, so up here it was 1 atmosphere, at 10 meters, you add an atmosphere, it's 2 atmospheres, you go down another 10 meters, you add another atmosphere, 3 meters of pressure. If you take a breath down there at 3 atmospheres of pressure, and then you hold your breath while you rise up quick to the surface, now the pressure in your lungs is 3 atmospheres, and the pressure outside is 1 atmosphere. Your lungs are going to expand by a factor of 3. That's not going to be good, right? This is why you should always exhale when you're rising from a dive. Personally, I'm a little claustrophobic, and the thought of going that far under the water gives me the willies. But there's a reason why you have to take all sorts of classes and get certified before you go scuba diving. Because there's so many things that you make a little mistake and boom, you're dead. So we could answer weird questions like this one. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere to an unknown depth. My question is, why? The volume of the air in the syringe at this depth is 7.5 milliliters. What's the pressure at that depth? Some of these weird questions you may need to draw pictures. So there's my syringe, and I've got air in there. And so up at the surface, that was 16 milliliters. And then we go down. I'm leaving the needle off because that wouldn't be very safe. We go down, and now the volume has gone down to 7.5 milliliters. Why did the volume decrease? The pressure of the water is pushing on it. That's air, it's compressible. So the pressure of the water is going to push that plunger in and it's going to decrease the volume. So this was the pressure at, the volume at 1 atmosphere. And down here, we want to know what the pressure is. Let's use the equation. Great idea. P1V1 equals P2V2. We need to take those numbers and identify them. We need to label them. You shouldn't label people, but it's okay to label numbers. Okay, so 16 milliliters. Is that a volume or a pressure? That's a volume. So I'm going to call that volume 1, because that was where we started. And this is pressure 1. Pressure 1. Those two go together. That's not pressure, it's volume. Volume 2. And then this must be pressure 2. So I've identified what those things are. I've given them labels. And then I use my equation that relates P1, V1, and P2, V2. I need to rearrange this equation. So I want to solve for P2. There are different ways to approach this. I'm teaching you what works for most students. If you have another way that works for you, great. You just need to be able to write it out clearly so I can understand it. So I'm looking for P2. Don't plug numbers in here and then rearrange it. That's a disaster. Rearrange it while things are simple and then put the numbers in. So I want to get P2 by itself. I'm going to divide by V2. Because the V's cancel out, V2's cancel out. So I get P2 is equal to, copy these down carefully because it's easy to get the numbers switched, P1, V1 over V2. And then I'm just going to take my numbers with their units and plug them into my equation. Pressure 1, 1 atmosphere. Volume 1, 16 milliliters. Volume 2, 7.5 milliliters. What happens to the units? Milliliters cancel. I'm left with atmospheres. I'm looking for a pressure. I got a pressure unit. That's good. So 1 times 16 divided by 7.5. 2.133 repeating atmospheres. Ooh, I was sloppy. This is 1.0 atmospheres. How many sig figs should that answer have? 2. So 2.1 atmospheres.
So
how deep would the diver be? Yeah. So if the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? 1 atmosphere for every additional 10 meters. 1 atmosphere per 10 meters. So 1 atmosphere per 10 meters, or 10 meters per 1 atmosphere. Is this the additional pressure? The 2.1 atmospheres? No. At the surface, what was the pressure? It wasn't 0. It was 1. So he's gone down. He's gone from 1 atmosphere to 2.1. So if I subtract what it was at the surface, I get that he's added 1.33 atmospheres. That's the increase in pressure. I can use this as a conversion factor to make that pressure change into a depth. So I've got 1.133 atmospheres. Atmospheres cancel out. So 11 meters. Any questions? I really should watch the show MacGyver sometime. I know what it means to MacGyver something. It means you rig stuff up, right? And so you could take an empty syringe, fill it with air. It's not really empty then, is it? But a syringe full of air. You'd need a cap on the end, not open. And if you're diving and you want to know how deep something is, you could go down and make a note of what the new volume of the air was. And then you could do a calculation like this and figure out how deep it was. There are simpler ways, like buying a gauge. You can buy stuff, but you could do it. Any questions?